So we're in section 6.8, and we're going to be talking about natural logarithm and natural exponential functions. These are pretty familiar to us from our study of algebra, right? We learned back in probably college algebra that the exponential function, base e, which we sometimes call the natural exponential, and the logarithm function, base e, which we always write as the natural logarithm function, are actually inverses of one another. And in algebra, you typically learn about e to the x first, and then you just define the inverse as the natural log function. In actual fact, it was the natural log function that came first in this chicken and egg story, and the exponential, the e itself, was derived from that. We're not going to go through all the details here. There's a lot of very, very theoretical math in this section. If you're interested in it, I would encourage you to read through the section in your book. But what I'm going to do is I'm going to give you just a couple of the highlights of where the natural log and the e come from, using a little bit of a picture and a little bit of geometry. And then we're going to go on and we're just going to review the rules for taking derivatives and integrals with these things. So a lot of what's done in this section, a lot of what you actually have in your notes here, I'm really going to skip over, and we're just going to hit the highlights. All right, so when you think about these two functions, one of the things I want you to think about is when you first learned about them, very likely your algebra teacher kind of avoided or was a bit vague about where that number e really comes from in the first place, and why we would call them a natural log or exponential. Doesn't seem like there was anything natural about that weird number, 2.718 blah blah blah, right? Well, the reason that people have to be vague about that in algebra is because we actually need calculus to understand where these functions come from. The true definition of the natural log function is an integral. The natural log of any number x greater than 0 is defined as the natural log of x is the integral from 1 to x of the function 1 over t dt. What does that integral really mean? Well, the integral is an area under a curve, right? So the function y equals 1 over t looks like this. It would have another piece down here as well, but we're just going to stick with positive numbers here. And let's see, if t is 1, this is the t-axis, this is the y-axis. If t is 1, 1 over 1 is also 1. So we're starting from 1 right here. And then we're saying, find the area under this curve from 1 until some arbitrary value x. So in fact, the natural log of x is just that area, the area from 1 to x under the curve y equals 1 over t. As x gets bigger, the natural log of x also gets bigger because there's more area. As x gets smaller, it gets smaller. Notice the natural log of 1 would be the integral from 1 to 1, which is 0, right? That's consistent with what we know about the natural log. This seems to fit what we already know. Also notice this area continues to get bigger, but it gets bigger more and more slowly because we're only adding a little area as we go out. So if you think about that natural log graph, it increases, but it increases slowly. So that's also consistent with what I see here. All right, again, I'm not going to get into all the really deep mathy things. There's several proofs on the next page that we're not going to do, but they are in your book, so I would encourage you to look into those. But what I do want to do is I want to take a look. I'm going to skip over a bunch of this stuff, just call your attention to things that I know you already know. While I won't prove it, remember that we have these really useful properties of natural logs, right? The product property, the power property, quotient property, right? Those are algebraic things that can actually help us out a lot when we're doing calculus, and we'll talk about that in a couple of minutes. And then, of course, we also know the derivative of the natural log function is 1 over x. Based on the definition of the natural log that we were just talking about, that should make sense, right? The derivative of ln x, the derivative is the inverse of the integration, so we just get 1 over, we plug the x in for t, and that's it. All right, the only other thing I want to mention before we just do a little bit of practice with our logs and exponentials is, what about e itself? Where does that come from? Well, e, as we know, is actually the inverse. The exponential function is the inverse of the log function. But in actual fact, we can use the graph again to talk about what e kind of looks like geometrically. Remember again, we had the natural log of x was defined as the integral from 1 to x of 1 over t dt. So, if I take the natural log of e, that would be the integral from 1 to e of 1 over t dt. And if these are going to be inverses, that's really e to the first. The actual log of e is 1, right? So in terms of my picture, my graph that I drew before, y equals 1 over t, starting from 1. If I go from 1 to e, the area under this curve has to be exactly 1. So that's technically the definition of e. E is the value that you would have to set so the area under the 1 over t curve gives you exactly 1. So much for the little bit of theory I wanted to talk about here. As I said, I'm actually not going to spend much time with that. Instead, we're going to concentrate on just reviewing the integral and derivative rules for this section. That's where your homework's going to be. So I didn't leave you a ton of space here, but on page 42 there's a little bit of blank space that talks about examples of derivatives and integrals using natural log and exponential functions. I'm actually going to do this on separate paper, and if you've got some blank paper you might want to do that as well. Let's review our derivatives and integrals for logs and exponentials. I'm going to start with some derivatives. And on your derivatives rules sheet, I'll be using these 4 derivative rules. These 2 you're really familiar with. Once in a great while, we talk about a base other than e, and we get this extra little correction factor of ln a in here. So we'll see a couple of examples of those as well. All right. So let's start with some derivatives. Start with a relatively simple one. Let's take the derivative of e to the negative 10x squared. Anytime you take the derivative of an exponential, first of all, of course, you just get the same thing right back again. And then we have our chain rule piece. The derivative there would be negative 20x to the first. And usually we like to write our final answer with the multipliers out in front and the factor that's exponential at the end. No big deal. Let's do a problem where the base is not e. Let's try the derivative of 6 to the ln x power. Now notice, according to our little list here, When we take the derivative of any base to a power, again, we start by getting back exactly what we started with. So my first part of my derivative is still going to be 6 to the ln x power. I then have a multiplier of the natural log of the base. So in this case, that would be times the natural log of 6. And then don't forget your chain rule. The derivative of ln x would be 1 over x. So I'd have 6 to the ln x, ln 6 over x. All right, one thing to always keep in mind when you're taking derivatives of log functions, which we're going to start next, is don't forget about those properties of logs, the power property, product property, quotient property. Sometimes they can save you a lot of work in your derivatives of integrals if you remember to use them. Let's take the derivative of next of the natural log of sine x cosine squared x. If I were to do this problem the way it's written, notice that I would have a product rule inside my log. However, if I apply the product property first, just doing algebra now, I'm not doing any calculus yet, I could rewrite this as the natural log of sine x plus the natural log of cosine squared x. That's better already. I'd always rather take the derivative of a sum rather than a product, but I can even do a little bit better. That power is really on the whole cosine, so I could bring that down in front. So I could use the power property to simplify even further. Again, I haven't even done the derivative yet. That becomes 2 times the natural log of cosine x. All right, now that I've done all that, my derivative is actually much easier to deal with. The derivative of natural log sine x would be 1 over sine x. And then chain rule, derivative of sine x is cosine x. Plus 2 times, and then same idea. The derivative of the natural log is first of all 1 over the argument, which would be cosine x, times chain rule, derivative of cosine x is minus sine x. So I get cosine over sine, that would be cotangent x, minus 2 times sine over cosine is tangent x. All right, let's do a few more derivatives, then we'll turn to integrals. What if I want, and I'm going to do 2 kind of related ones here. I'm going to do the derivative, first of all, of the natural log of x squared plus 5 to the 3rd power. Once again, this is going to be much easier if I start by applying my power property and bring that 3 down in front. Now instead of a double chain rule, I just have a single. So I've got a constant multiplier of 3, derivative of the natural log, 1 over that x squared plus 5, and then chain rule would be a times 2x. So I'm going to end up with a 6x over x squared plus 5. I'll put this next one right next to it because I want you to really see the difference. What if I change the looks of this problem just slightly? What if I want the derivative of the natural log cubed of x squared plus 5? Just like trig functions, when I put the cube on the function itself, what that really means is the whole log function is cubed. Now be careful with this one. I cannot apply a product property here. The product property is what I use when the power is on the argument, right? This x squared plus 5 was inside the log, and I'm only cubing the argument. Here I'm cubing the whole log function, so I cannot use the power property. It does not apply. Instead, I'm just going to go right ahead and do my derivative. Now, the derivative rule for powers says bring down the 3 and reduce the power by 1, right? So first I'll get 3 times all of this. Squared. Then, chain rule, I take the derivative of what's inside. The derivative of the natural log would be 1 over x squared plus 5. And then one more chain rule, the derivative of the x squared plus 5 is 2x. So I end up with 6x times natural log squared of x squared plus 5 over x squared plus 5. Okay. So do watch out for that. Make sure, if you're going to use a power property, that the power is on just the argument, not the entire function. All right, let's go on and start talking about some integrals that involve exponential and logs. I'm going to start with the integral of x squared. Actually, let's make that a 10 instead of an e. Times 10 to the x cubed dx. Hopefully, as you're looking at that, the first thing you're thinking is, oh, I see the u substitution here. Derivative of x cubed is 3x squared, and we've got the x squared, right? So let's start with our substitution. Du would be 3x squared dx, and 1/3 du is equal to x squared dx. I've got the x squared dx right there, so I'll be replacing that with 1/3 du. So we've got 10 to the u, and then a 1/3 du. And since this one is not the natural exponential, or natural log function rather, probably need to look this one up. If I've got a base other than e, I do get the a to the x back again, so I am going to get the 10 to the u back again. But then I have to divide by ln a, so in this case that would be ln 10. So let's see. I would have 10 to the x cubed power over 3 natural log 10 plus c. All right, let's try a few more integrals. This time let's use the natural exponential. Let's integrate e to the sine x times cosine x. dx. Once again, what's in the argument, or in the exponent rather, is probably going to be a good choice of u. The derivative du is exactly cosine x times dx. So I don't even need to fix anything this time, right? I've got my exact du sitting right there. So this is just the integral of e to the u du. Our favorite integral because it is the only function whose integral is itself. E to the u, or e to the sine x, plus c. All right, I always find those exponentials usually nice to integrate. It's pretty obvious usually what the u needs to be. Let's look at a couple of other kind of common tricks or tips I can give you for integrals involving exponentials and logs. This next one, let's try the integral of log base 3 square root x over square root of x dx. Just like what's inside the exponential, in this case sine x, what made a good u, what's inside the log also often makes a good u. So let's give that a try. Let's let u be the square root of x, or x to the 1/2. Then du would be 1/2 x to the negative 1/2 dx, or 2 du equals, that's really 1 over the square root of x dx. And I've got that, right? That square root of x is in the bottom. Put that with the dx, and I can replace that with a 2 du. So I've got the integral of log base 3 of u. And again, I'll replace this with a 2 du. All right. When I have a base other than the ln, the base e, I probably need a little help here. Let's see. Oh, you know what? I don't think that one's even on here. I probably made up not such a great problem. You know what? I'm going to have to say we need a little bit more information before we're ready to do that one. We need to know how to integrate a log. And that was my mistake. We haven't not yet learned how to do that. That actually comes in Chapter 7. So we did set up our use substitution correctly, but we're stuck at this point. We don't have enough information to go further. Sorry about that. Let's try another one. Let's take the integral of the natural log of x squared plus 4 over x dx. On this one, I once again am seeing a power property. I could bring that 2 down in front. That's going to make this look a little simpler. So let's do that. Make that 2 ln x plus 4 over x. All right, now I need a good choice for u, and I claim this time I think the whole numerator would make a good u, because the derivative of ln x is 1 over x, and I've got an x on the bottom. That's very encouraging. So let's let u be the whole top of this fraction. The derivative, so du is going to be 2 times 1 over x, and of course the derivative of the 4 is 0. I'll bring the dx over here. So 1/2 du is 1 over x dx. I've got the x in the denominator as well as the dx. So again, I'm in good shape. I'll just replace that with the 1/2 du. So the whole numerator is my u. Everything else becomes 1/2 du. And I can just integrate that. Integral of u would be 1/2 u squared plus c. So I'm going to get 1/4. And let's see, the u was actually 2 ln x plus 4 squared plus c. All right, last couple of integral examples coming up here. Oops, this is actually number 5. If we include the one that didn't work, right? Number 5. I would like to integrate secant squared x over 1 plus tangent x dx. Another good choice for you is what's in the denominator. And in this case, I like that one, because if I let u be what's in my denominator, I know the derivative of tangent is secant squared, and I've got that. So let's try it. du is just going to be secant squared x dx. And I've got everything I need. If I didn't, this wouldn't work, right? But I got it, so we're good. I've got the u on the bottom. Secant squared x dx is du, so just a 1 left on top. And the integral of 1 over u du is the natural log of the absolute value of u, or in this case, the natural log of 1 plus the tangent of x, plus my constant of integration. All right, one more example. This last one, I'd like to integrate e to the 2x minus e to the negative 2x over e to the 2x plus e to the negative 2x dx. Looks a little complicated, but I'm going to try the same trick as we used in the last problem. I'm going to let u be the denominator. The derivative would be, it'll be e to the 2x times 2 for the chain rule. And this will be e to the negative 2x times negative 2 for the chain rule. Times the dx. And that is pretty close to what I have up here, right? If I factored out the 2, I'd have it. And then I'm going to go ahead and divide the 2 over to the other side. So all of this becomes 1/2 du. That u is in the denominator, and I'll just make it 1 over u. All of this gets replaced with a 1/2 du. And so my integral becomes 1/2 natural log u plus c, or 1/2 natural log e to the 2x plus e to the negative 2x plus c. Tempting, natural log and exponential being inverse functions. The problem, of course, again, is the addition. I can't distribute the natural log. It doesn't make sense to even say it, really. So I'm stuck with this. There are no log rules that allow me to separate a sum, only a product or quotient. All right, so a combination of using your log rules to simplify things before you take derivatives and integrals, along with the application of our regular integral and derivative rules, is how you're going to do these. Mostly this will be a review section, since we did look at these kinds of integral and derivatives in Calc 1.